is that there's no shared state between tasks. In this example code, I'm trying to share some state between two tasks by taking a pointer to it and passing it into a different task, who will then modify it. Somebody with a sharp eye for concurrency will think, oh, this is a data race. You don't know whether 0 or 1 is going to get printed from the debug statement. And in fact, this program fails to compile. Rust-C tells you that state pointer is not a sendable value, which means that you can't send it between tasks. So what can you do? How can you have tasks communicate with each other? If you were here last week, you saw Eric Hulk present on pipes, which is our wonderful concurrency primitive for message passing between tasks. And the key point is that when you send state to another task, you give up ownership of the state. So here's some code. I'm creating a stream of pipes with a send end and a receive end. I hand the receive end to a child task, and I send a string on it. I don't have access to the string anymore, and the child task sometime later will. So this is all great. My contrived examples make sense. But let's put tasks to the test. Let's suppose that we were writing a web browser in Rust. Well, if you were here last week, you would know that we actually are. It's called Servo, and it makes heavy use of tasks. How might you want to use tasks in real-world application development? 3 examples. First, you definitely want to render different content elements on a web page in parallel. There's no reason to block on network I/O in serial for each content on the web page. So here I have a web page with 3 images. They're each partially loaded, and altogether they'll all finish loading a bunch faster if I parallelize them with a task for loading each one. Another example is having pipeline decoding of HTML and CSS. Instead of parsing it in one phase, and then after that finishes, lexing it afterwards, Servo has the ability to parse and lex in parallel. The lexer processes the parser's output before the parser's even finished. So there's a parser task, there's a lexer task, they operate in parallel, and the whole operation completes a lot faster. A third example, if you're the sort of person who uses a million tabs for as many different things that you're browsing at once, you might want to use a browser that uses one task per tab, so that each task doesn't have to serialize around the other tab's activities. Now, this is all well and good. Let's say that we have a browser that uses tasks for everything, and it's parallel and wonderful. We've still missed something, which is that sometimes things go wrong. And we have to set up our tasks to be able to handle failure properly. It turns out that when things go wrong, there are different ways in which they go wrong. And as any experienced programmer will know, you have to sit down and think about what the right action to take is, instead of crashing your program wholesale or ignoring the error wholesale in all cases. So for example, you might have, the user causes your program to abort by killing the program, by closing a tab. You might have a logic error in your program, an assertion trips and the program crashes. You might have malformed input if you're visiting a badly programmed web page. You might have a bug in other software, like if you're trying to direct render some 3D graphics and the graphics driver is written by, won't say names. So what I did was I enabled tasks to have different failure propagation modes. We now have 3 different main spawn modes for tasks. You can spawn a task supervised, which means that if the parent task fails, it will propagate and take out the child as well. You can spawn tasks linked, which puts all the tasks in the same linked failure group, which means that if any one of them fails, all of them will be taken out. Or you can spawn tasks unlinked, which means that failure in one task is isolated from failure in another. Now, in case you don't believe me, I'm going to motivate these use cases. It turns out that the 3 examples for tasks I presented before happen to map nicely onto the 3 failure modes. What a coincidence. So let's say that I have a main tab manager task for a web page that I'm loading, and it spawned 3 different image renderer tasks. And one of the images happens to be corrupted. Well, you don't want it to take out all the rest of the web page. You just want it to display an empty box to mark where that task failed. However, if the tab itself crashes, the user clicks the X button or the web page is malformed or something, you don't want to leave the image renderer tasks hanging around downloading data that nobody's ever going to see. You want the failure to propagate. Case 2, why would you ever want tasks that are bidirectionally linked to each other? Well, let's say that you're doing this pipeline CSS and HTML parsing, and the parser encounters some invalid input. There's a parse error, and the lexer, there's really no point for the lexer to continue, so you want the failure to propagate to the lexer. By the same token, if the lexer encounters some invalid HTML that was successfully parsed, there's no reason for the parser to go on processing the rest of the input stream because the lexer is never going to catch up. So you want failure to propagate bidirectionally in this case. Case 3, why would you ever want tasks whose failures are isolated from each other? Well, if you've ever opened a web page with some graphics intensive work and maybe some untrusted plugins, you'll probably be familiar with this screen. If we had isolated tasks for each tab, you would see this screen a lot less. Only the tab would crash, the entire browser would not. So that's the 3 spawn modes. If you really want to get your fingers dirty, there are some extra advanced options, which you can chain together with a bunch of method calls all on one line, like this top line here. And in brief, you can configure the scheduler mode, which changes the scheduler behavior of the task. You can get an object called a future, which you can carry around and later call out to, which causes you to block until the task finishes. You can call try, which spawns the task much like the future, immediately blocks on it, and gives you a result which tells you whether it succeeded or failed. You can use some convenience wrappers for setting up communication with pipes between the tasks, so you don't have to repeat all the dirty work. So I'd like to thank the Rust team, especially Graydon for his leadership, and Brian for his endless patience answering all my questions about the Rust runtime during the first month or two. I'd also like to thank the Rust interns especially for being an excellent community. It's been a fantastic summer. Any questions?
So there's a fourth failure mode that you can sort of see from the 3 you have there, which I think is the child dies and kills the parent, but not necessarily the other way around. Is there any reason why we would ever want that? You know?
Well, I'm glad you asked that. I decided not to make this a primitive because, 1, it would be a lot harder to implement sort of in an integrated way with the other 3, and 2, because you can program it on top of the other 3 mechanisms that I said. So here's some example code that does that. You spawn a task linked to yourself, which spawns unlinked the child task, and communicates with the child task to see if it fails. If it fails, the middle task fails, which is linked to you, which kills you. But since the child is unlinked, if you die, it won't kill the child. So this is sort of a derived primitive from the other 3.
Like a macro.
Like a macro. Anything else? All right, thanks.
What's up next? That would be you. I think he's going to use it too, so we can just jump it up there.
Okay, I need to figure out how to disable those transitions.
Bonus slides before you ask the question.
No, I didn't.
Oh, I thought you two had set that up.
No.
Oh.
I thought that I accidentally set it up.
Well,
Yeah.
I have places where I have
Two are really
bullet
good.
points coming on all the time.
Yeah.
Mine, some adjective, mine's kind of like
Yes.
Intern mine, think of like.
I thought that was a spot.
You didn't get my other 2 bonus slides.
Anyway, I saw there.
We just write bonus slides for macros, where you like demonstrate the macro implementation of that.
I didn't write a macro until like yesterday.
know what the other bonus slides are.
You could have done it with a function though, right?
Done what?
Yes.
Child kills parent.
Yeah, I mean, that would be like the implementation.
Yeah.
First, how was he?
Yeah.
I like that.
Oh, he was in plus
parent,
one.
Okay. How do I
like,
get to
easily
go?
expressed in terms of the other one.
And then all the way to the
I don't
bottom.
think it's
That's what the slide show.
It bothers you that it's separate?
No. Makes me wonder why can't the others be expressed? Some core, I guess it's the unidirectional graph,
There, I think that's better, yeah.
directed graph failure.
I don't really want.
Bidirectional, so, well,
Child kills parent but stays alive.
well, it turns out that bidirectional, once you have that, then the
I
task
can
group
probably
becomes the
say
primitive,
something
and
Figure it out.
unidirectional failures between task groups.
I don't understand. Once you have what?
So, once you decide to implement bidirectional failure, then instead of the primitive being a task, the
An
primitive
inefficient
is
way
a
to
task
lay out a
group.
laptop.
Well, it could be like a touch screen with a keyboard that displays information.
And it could be one of those keyboards that has that like
Yes.
Like a player
like on
keyboard.
Optimus
Yeah, that
right.
makes sense.
Right,
the
there's one
with
like-
images on with
Oh,
say,
yeah.
with keys.
And then if you want to have
Or even
unidirectional
if it's just like
failure,
a player keyboard, like
it's effectively between task groups.
it communicates with you by
Within
depressing the
task
keys
groups.
in sequence.
So that's the way. to implement it.
Yeah, that
So
makes
like a
sense.
Ouija board.
Yeah, I just
want to ask, is this stuff in Rust already?
Yes,
It works.
yes. All of the code that I showed compiles and runs, except for the code that explicitly doesn't.
And does the right thing.
Yes, and it does the right thing.
He also implemented mutexes, or like reader-writer locks, so
Right.
you have like some shared data, which we've been using in Servo.
Yes,
Which is really nice.
that was one of my other bonus slides. If
Oh.
you want mutable shared state between tasks,
Right.
you can do that, and you can have like condition variables associated with the lock.
Right. And it's all proved safe, so you still don't have races, which is really nice. So just
Right. It uses the mutability in the type system, and also lifetime pointers to prevent you from getting the stuff to escape out of the lock.
I'm concerned you might have interpreted my comment as a criticism.
Ah.
It was not intended. I was wondering about maybe there's a fundamental mismatch. It doesn't really matter anymore.
I mean, I spent some time wondering if instead of implementing it like with exclusives, I could have done it with pipes, but
Oh, is that how you I was wondering how you, I didn't look at your slide closely enough, but when you're modeling child kills parent, did you use pipes to do that so the one end dies and you get a message or something?
I use task try, which uses pipes.
I got a 60.
Well, it uses ports and chans because it uses
And
the
it's
pipe.
my favorite element. What an excellent day.
But yeah, it uses yes.
Okay. Are we ready? Okay, so I'm Michael Sullivan. I'm on the Rust team, and I worked on a bunch of different things this summer, and I'm going to talk about some of them that I found most interesting. So first, I'm going to talk a little bit about what Rust is, then I'm going to talk a bit about how vectors work in Rust, because I worked a bunch on that this summer, and then what I'm calling static trait methods, and just sort of wrapping up with other things I worked on. As first, a disclaimer, Rust is still under heavy development. The things I talk about in this talk might not be true tomorrow, but they probably will, because we aren't, I don't think we're throwing away anything I've shown in this talk. But there's still a lot of churn happening. And you know, what I discuss and how I present issues reflect my personal biases in language design, which may differ from other more important members of the Rust team. Okay, so sort of goals. So what do we want in a programming language? Well, we want it to be fast. We want to generate efficient code for sort of obvious reasons. We want it to be safe. We want the type system to provide guarantees that rule out different bugs like buffer overruns and null pointer dereferences and various sorts of crashes. And we want it to be concurrent because, so, you know, for every talk about concurrency, there's sort of a mandatory graph of how Moore's law isn't working anymore. I'm leaving that out, but we want a language that makes it easy to take advantage of parallelism. And, you know, for us at least, we want something sort of systemsy. We want fine-grained control over what's going on and predictable performance characteristics. We don't want it, you know, doing lots of memory allocation behind our back. And so what languages do we have? Well, we have, you know, what we have Firefox written in now is C++, which is, fast and systemzy. ML is, sometimes fast and is, quite safe. Erlang is safe and concurrent. Haskell is, sometimes fast, very safe and also concurrent. And Java and C# are fast and safe, but also, are Java and C#, which have plenty of their own problems, right? So what we want is a systems language, pursuing the trifecta: safe, concurrent, fast. Okay, so some of the design issues in Rust, we have a lot of, fancy features in our type system. We have algebraic data types and pattern matching, a la ML or Haskell, which means we don't have any null pointers. So you never have a Rust program crash because of a null pointer dereference. And you have, sort of very high-level ways of operating on lots of different data. We have polymorphism. You can write functions that work over different sorts of parameters. We have, type inference. So, even though we're statically typed, you don't need to write the types over and over. We have this somewhat idiosyncratic type class system that we call traits that let you, write code that's parametric over types that have certain properties. We have a strong emphasis on immutability in our data structures, and we have what we call region pointers, which allow you to have, safe pointers into any object with a static borrow check that makes sure you don't access dead data. We have some other features like lightweight tasks with no shared state, which Ben talked about, fine-grained control over when you're allocating memory and when you're putting things in the stack, and the ability to, and Ben talked about this, to have unique pointers that you can move and send over a channel while giving up your own reference to them. Someone described it as like C++ grew up, went to grad school, started dating ML, and is sharing an office with Erlang. Sort of reflects some of the influences here. So our status, we currently have a self-hosting Rust compiler that uses LLVM as a backend. We handle our polymorphism by generating different copies of the code for each type parameter. This is similar to what C++ does for templates, but yeah.
Better.
Right. And memory management is currently automatic reference counting, which I have a distaste for, but that might be changing. The catch is, we're not done yet. There are lots of bugs and sharp edges. We're still changing rapidly, but we're getting really close. We're a lot closer than when I said this last summer. Okay, so I'm going to talk a little bit about the different sorts of heap pointers we have in Rust, and then a bit about what vectors in Rust look like. So first, well, obviously we want to be able to heap allocate memory. And we want that to be garbage collected. When nothing's using it, we want it to automatically be freed. We don't want C-style free, because then we screw that up and leak memory and crash and, access freed memory. It's just very bad, right? So we have what we call at pointers. Something that's of type @int is a pointer to a heap allocated integer. There can be multiple references to each object in this heap. When you copy it, you just copy the pointer. So there are multiple references to each object. Right now, when you copy it, you'll bump a reference count. But if we get rid of reference counting, it'll just be a copy. But you can't share these between tasks. We don't have a concurrent GC, and we don't have shared mutable, and we don't have shared state. Well, shared mutable state. So they can't be sent between tasks. And the problem is, sometimes you need to send things between tasks. So we have tilde pointers. And these are unique pointers that uniquely own the data they're pointed to. It's owned by one pointer. If you copy one, you have to allocate more space and copy the underlying data. But the advantage is, since there's only one of them, if you give up your reference to this and hand it to someone else, you know that now they have the only reference, which makes it safe to send across a channel as long as you give up your handle to it. So these are useful for inter-task communication. Now I'm going to talk about how these different sorts of ways to heap allocate impact vectors. Because you wind up with a choice. If you want heap allocated vectors, which heap do you put them in? And so we have, braces of T is considered to be the type of vectors containing some type T. But the problem is vectors can have any size, right? Their size is based on their number of elements. So you can't just put this on the stack and copy it around because you don't know how big it is, you don't know how much memory to reserve. So they're what some of us call at least, a second class type. These vectors can only appear when they're pointed at by some sort of pointer, and that can be an at pointer or a tilde pointer, or I haven't really talked about them, but region pointers. In memory, a vector has a size field, a field for how much of the space has actually been allocated, and then a buffer of allocated memory. And these will be living inside heap objects, or mainly they'll be living inside heap objects in either the at or the tilde heaps. But so then, how do you actually use them? Okay, so here's some simple code that uses vectors allocated on the unique heap. And you can see here we create a new empty vector, and we iterate through all of the numbers between low and high, and each time we push that element onto the vector. And it's safe for us to modify the vector in place like this because we know that there's only one pointer to the vector. V has to be the only pointer to that. And so if you need to reallocate it, reallocate space because you're growing it and that moves it, you know that there's only one reference to it, and so you can update it. So it's with these unique pointers, it's safe to do that. But this trick doesn't work with an at vector, with a vector pointed to by an at pointer, because the problem you run into there is that there could be multiple pointers to that vector. And if you have to move the object in memory because you need to resize it, you can't possibly find all of those and update it. And furthermore, some of those pointers, might be immutable pointers. They think that the array is not changing. So it doesn't work at all. We can't modify it, we can't resize it. But building up a vector by pushing elements on the back seems a very natural way to build arrays up in an imperative style, like we showed in the previous slide. So if we know for sure that there's only one reference to this vector, then we can get away with pushing onto it. So we could build up safe abstractions that sort of have hidden away a reference to an at vector. And if it knows it's the only one, it can go do some unsafe stuff under the hood to push it on. And then when you're done, you can ask for the at vector out. And this would be something like Java's array list, right? Where it has an array under the hood, and you go through this object that mediates your accesses to it. But this is somewhat unsatisfying, though. For some reasons I'll get to later when I talk about static trait methods, but also just sort of from a philosophical perspective, it bothers me that there's no nice way to construct these objects directly. I don't think it should need to be mediated through this other thing. So I came up with a nice interface for building this sort of vector. That's a function called build, and it takes as an argument a builder function that it calls with a push function. And what builder does is it is executed for its side effects, but at any time it can call the push function it was given as an argument, which will add some new element to the end of an array. So build allocates a new vector, which it doesn't give to anyone, but then calls builder with a function that when called pushes onto this vector that build has hidden under the hood. Build has the only reference to it, so you know that if it needs to resize it, it can do that. No one else can be using it. And so the code to implement this is very unsafe and does a lot of nasty hacks, but the interface is completely safe. This is a third order function, which makes I'm a functional programmer out of academia, so this makes me very happy, right? The more higher order you can get, the better, right? So if that seemed too complicated, it's not really. If you look at the code, it seems pretty natural. You say like I want to build up an array, so you call build, and you get back a push function, and then you just go basically write the same code that you wrote for building up the tilde vector. the type signature looks a lot scarier than the actual code does. The code, seems fairly natural. The biggest downside is you sort of have to indent your code 4 spaces, which when you're working on a project with a hard 78 character column limit is maybe a big drawback. But so this seems like a fairly natural idiom, and lots of other primitives can be built on top of it. Basically, anything you want to build up a vector, or most sequences really, can be built on top of this notion of pushing things on the back. There are just lots of other higher and lower in certain ways level primitives you can build on top of those. So now I'm going to talk a little bit about traits. And Lindsay Cooper gave a talk about this last week, but I don't know how many people remember that, so I'm going to talk about them a little. And traits are just interfaces that specify a set of methods for types to implement. And then functions can be written that are parameterized over any type that implements that trait. This is just like type classes in Haskell, and is somewhat related to interfaces in Java also. This is something that's, again, easier to understand with an example. So here we can define a trait called show that has one function, show, that when called creates a string formatting the object. And so here we have an implementation for int and a function exclaim that is parameterized over any type t that implements show, and it will take that, format it, and then add an exclamation mark to the end. And you can see these typeclass methods are called with sort of an object-oriented style dot notation, where you call x dot show, and that's how you call it. And so this sort of thing is useful in a lot of places. But there's sort of this annoying limitation with our trait system, which is that traits contain methods, and they're called in dot notation. And since they're called in dot notation, they all require as their first argument an element of the trait type. And there are plenty of places where you want to be able to not just, modify or access any objects in a type parametric way, but you want to be able to create them. So consider, for example, you want to define a trait that lets you read elements of some type from a string. You want to be able to say, I want to be able to read in, a generic way where you are given a string and it can read back any type. There'll be some code demonstrating what that would look like. But so I solved this by adding static trait methods. So we added a static keyword that can be applied to trait methods. They don't take a self parameter like other methods and can't be called with dot notation, but they're treated as a regular function sort of in the parent namespace of where the trait's defined. The function then gets parameterized over the trait type. So you call it like a normal function, and it can operate on any type of that trait. This is, if anyone's familiar with Haskell, sort of the norm in Haskell. This is how all type class functions work in Haskell. They don't have this notion of methods that we have. So we can define a trait read that has a static function string that takes in a string and returns self, which means the type that the trait's being declared for. And read will have the type signature where it is parameterized over any t that implements read. And for any t that implements read, it takes a string and gives you back a t. Now, sort of bringing this back together with what I talked about in the vector section, we can take that interface I came up with for defining @vectors and generalize it. So we can create a trait buildable that has a function build that calls a builder function with a push argument and returns back something of the trait type. So now we can write this sequence range function that operates over any buildable type. So now you could call this and have it produce an @vector or a tilde vector or a linked list or a set, or basically anything where you can define this notion of pushing an element onto it, which is a very powerful notion. So that's a brief overview of static trait methods. I worked on a bunch of other things this summer. Some much bigger than those, but, well, some of them more time-consuming than those, at least. But those were the most interesting parts. I made a lot of major syntax changes to vectors and strings and sort of normalized all of them before vectors were sort of implicitly assumed to always be on the unique heap, and I got rid of that. I added compiler diagnostics to prevent implicit copying of mutable data and data allocated on the heap, so that you wouldn't accidentally be copying mutable data, which is usually a bug, or accidentally doing copies that require new heap allocations, which is a major performance hazard. And I'm working on adding a notion of explicit self-parameters, which sort of generalizes the notion of methods so that the methods can take as their first argument a type that's not exactly the self type, but is instead the self type with a certain sort of pointer to it. And I've also fixed a lot of various bugs in the Rust compiler and the Rust runtime. My goal was a bug a day for the summer, but I've fallen somewhat behind that. I think I'm at 44 and we need 53 right now to have kept up. Okay, so sort of in conclusion, Rust is a new systems language out of Mozilla Research that's designed to be fast, concurrent, and safe. Worked on a bunch of different stuff this summer. Third-order functions are apparently useful for constructing arrays imperatively. And our traits between my work and Lindsay Cooper's work, which she presented last week, are almost as cool as Haskell 98's type classes. If you look at modern Haskell with GHC extensions, they have a lot of type class features which I don't think we have any interest in trying to mimic. But if you look at their base stuff, we've got most of it now. Okay, any questions?
How many of those bugs did you open for the purpose of maintaining a one bug a day?
A bunch of them. I mean, but they were all bugs I fixed, right? Right, they were all actual bugs. I did not introduce any bugs so that I could fix them.
Like none were open saying like, I need a bug for today, and they
Right,
closed.
right. I never did that. They were all actual bugs I found. And it's definitely the case that like when I found a bug, I opened a bug and then fixed it so that there'd be a record of me having fixed it. But all of these correspond to actual bugs I fixed. Okay, anything else?
Curious, what are the missing features from Haskell 98's type classes that you would?
So right now we don't have inheritance yet, but we're planning to get that soon, like type class inheritance. The other big one is since we don't have higher-kinded type constructors, we don't have higher-kinded type classes. And if you look at Haskell, a lot of their most powerful type classes are higher-kinded, like monad. We can't implement monad in Rust's type class system, which, maybe that's fine. Okay.